So far in your single variable calculus courses and in this course, you've only seen functions of single variables. In single variable calculus, for example, you've seen functions that take some subset of the reals as an input. You take D, there's a subset of R, and have a function that goes from D to the reals. So for example, if you have y equals 1 over 1 minus x squared, right? So let's call this f of x. Then the domain of f of x equals the real numbers minus plus 1 and minus 1, right? The point is that this takes in single variables and outputs. It just takes in real numbers and outputs real numbers. You've also seen in this course, you've also seen vector functions. What do vector functions do? Vector functions take in real numbers in their domain and output ordered pairs of real numbers, right? R3, R2, Rn, etc. You've seen functions of the form Rt equals f of t, comma g of t, comma h of t. Right, so this domain should actually be written as d. Right, it's not the entire set of real numbers. So the domain of this function, domain of Rt, equals the domain of ft, domain of R, not of Rt, of R, equals the domain of f, intersection the domain of G, intersection the domain of H. Now what's different about functions of several variables? What's different is that now our functions are going to take in more than one variable, right? So they're going to take in ordered pairs, right? First let's define what an ordered pair is. Ordered pair. Pairs, right? X, Y. First of all, why is this an ordered pair? This is an ordered pair because X, Y is not equal to Yx, meaning this is not a list. This is not a list. So I mean, it's not a set, right? So these are ordered pairs, and of course, X is taken from the reals. Y is taken from the reals. So XY is taken from R2, meaning this is the Cartesian product of R and R. Just keep in mind that an ordered pair is a list of items, right? I mean, is a pair of things where the order matters, right? The thing, the object in the first slot, X is X, and the object in the second slot is Y. Okay, so how do we using this, how do we define a multivariable function, right? So a function, a function of two variables. How will we define it? So a function of two variables, a function f of two variables is a rule, right? This is a rule that takes in ordered pairs, right? Ordered pairs x comma y of two variables and gives you a real number. So the domain of this function, the domain of f, right, is a subset of R2. Domain of f is a subset of R2. Now, for all you know, it might be R2 itself, but it is always a subset of R2. Okay, so what f does is it takes you from D to R, of course from its domain, to the set of reals. Now this can be represented diagrammatically as follows. You draw the axes first, to the y-axis, you have the x-axis, the origin, x, y. You take this to be the domain, for example. Right, so you can represent, since as ordered pairs of two numbers, you can represent the domain diagrammatically. Just draw a few lines here to represent that this. Want to represent that this area, the shaded area, is the domain of the function. Let's call it. Let's give it a name. Call it D for domain, and the output is going to be on the number line. On the number line. So, for example, if you have a point P, label it x1, y1. This output is, of course, then f of x1, y1. Let's say a point Q, x2, y2. The output is f of x2, y2, and so on and so forth. Right? Now, notice that, and it's important to notice this, that in general, and keep this in mind. F of AB is not equal to f of BA. Okay, so this is important to keep in mind. Because why is that? Because remember that because they're ordered pairs. Because we are dealing with ordered pairs of numbers in our domain. Okay, so let's look at a few examples of a few examples of functions of two variables, and let's try to sketch their domains. So, so the first example given in your textbook is fxy equals fxy equals the square root of x plus y plus 1 divided by x minus 1. How will we calculate its domain? It's a square root in the numerator, and there's a polynomial expression, meaning a linear expression, in the denominator. So because of the fact that there's an x minus 1 in the denominator, I can safely say that x is not equal to 1. So x equals 1 is excluded from the domain, right? And I can also state that because of the existence of the square root, I can also state that x plus y plus 1 must be greater than or equal to 0. In other words, y must be greater than or equal to negative 1 minus x. Okay, so the domain is basically the domain of this function, domain of f of xy, is equal to R2 minus the pairs of functions, the pair. Okay, let's put it this way. All ordered pairs xy, such in R2, except for with the condition that x is not equal to 1 and y is greater than or equal to negative 1 minus x. So that is the domain. Let's sketch the domain of this function. Y-axis on the x-axis, the origin, y, x. So x is equal to 1 must be excluded from the domain. Let's indicate that by a dashed line. Dashed. This is the line x equals 1. X equals 1. And the region y is okay. So the region y is greater than or equal to negative 1 minus x can be indicated by let's draw the line first. Draw a line. So this the line y equals negative 1 minus x has I mean, when y is 0, x is obviously equal to negative 1. So the line looks like this. Right, so this is that line. And then and everything within the so everything in the region that I'm going to shade is included in the domain, except for x equals 1. Right? Everything in this blue shaded region is in the domain, except for x equals 1. This diagram represents the domain for this is the domain of f of xy equals the square root of x plus y plus 1 divided by x minus 1. Okay, so there are functions. There are other functions that, I mean, you could find the domain of any function of two variables. I mean, if you know the domain of a function of two variables, you can sketch it on a flat piece of paper. That's it. For example, the function f of x equals the square root of 9 minus sorry, this is not f of x, this is actually f of x comma y, right? F of x comma y. Remember, we're dealing with functions of two variables, so this is the square root of 9 minus x squared minus y squared. So because of the existence of the square root, this must be greater than 0. 9 minus x squared, the argument in the square root must be greater than or equal to 0. And this tells me that x squared plus y squared must be less than or equal to 9. Right? This is the domain. Right? X squared plus y squared is less than or equal to 9. So the domain is then geometrically speaking, the domain is the set of points on the circle x squared plus y squared equals 9 and within it. Right, so that's the domain of the function. Okay, so okay, let's what about the range of this function, right? The range of this function, this is the positive square root, right? The range of this function is the highest value that this can take, right? That this function can take is, remember, x squared. Let's find the range, right? X squared is greater than or equal to 0, right? And y squared is greater than or equal to 0. So this tells me that 9 minus x squared minus y squared is greater than or equal to 9. Sorry, is less than or equal to 9. This is less than or equal to 9. This tells me that the square root of 9 minus x squared minus y squared is less than or equal to 3. Okay, and of course, since this is a positive square root, this must be greater than or equal to 0. So we have the following lower and upper bounds: 0, 9 minus x squared minus y squared, 3. Right? So the range of this function, the range of f of x equals 9 square root of 9 minus x squared minus y squared, is range of f is between 0 and 3. Alright, cool. So now let's try to graph our functions of two variables. So if we graph a function of two variables, we get a surface in 3 dimensions. When we graph a function of two variables, you get a three-dimensional surface graph, a function of two variables you get a three-dimensional surface. Right, so for example, let's look at this simplest possible example, that of a plane. Right, so you have f of x comma y equals 6 minus thrice x minus twice y. Now, once we know 3 points on the plane, we know the equation of the plane. So let's make the plane. Right, so you have z-axis, x-axis, and the y-axis. This is a right-handed coordinate system. Z, x, y, you have the origin. Right, so so this plane, right, when x equals 0 and y equals 0, then the plane then z equals 6, right? So f of 0 comma 0 equals 6. Right, so this plane, of course, passes through 0, 0, 6, and then when x equals 0 and z equals 0, when x equals 0 and z equals 0, then y is equal to 3. Right, so this plane then passes through 0, 3, 0. And when x equals when y equals 0 and z is equal to 0, then x equals 2. So this plane also passes through 2, 0, 0. Right, so let's finish the plane. Finish the graph of the plane. Let's connect this to this. I mean, the triangle is part of the plane, but it's not the entire plane. Let's shade it using blue. So this is a sketch of a part of the plane. Right? Sketch. Of a part of the plane. In this course, we're not going to be sketching. I mean, we will need to be visualizing surfaces. We will need to be visualizing because we'll need to be calculating volumes of integration. But later on, I'll show you how to draw surfaces using Mathematica. Right, this is a far more efficient method than just sketching. Right, so let's look at the function, the sketch of the function given by g of xy equals 9 minus x squared minus y squared. Right, so you have g of xy equals the square root of 9 minus x squared minus y squared. Now, as we saw before, the domain of g of xy is the circle, is everything on and inside the circle of radius 3, centered at the origin. So let's what we're going to do is we're going to try to sketch the surface that is given by g of xy. We'll sketch the surface given by g of xy. And I guess that will do it for this chapter, for this section, 14.1. I want to skip contour plots. Sorry. So we have Z. X, Y, Z, the origin. So g of xy is going to give me a hemisphere, meaning half a sphere, above the origin. I'm sorry, above the xy plane. This is going to give me a hemisphere. Write this in red. Hemisphere above the origin. Let's see what that hemisphere looks like to us. So of course the thing is that it's going to be a circle on the domain, right? And this is the hemisphere, right? And the projection of that hemisphere on the xy plane, sorry, the hemisphere not above the origin. The hemisphere is above the the correct way to frame this is the hemisphere of the xy plane. So this is z equals g of xy. Z equals g of xy. This is z equals g of xy. Right, so there are much more complicated shapes that you can draw. We won't be doing those manually. We'll try to use Mathematica or some other graphing software to draw these shapes. Contour plots, level curves, and contour plots I'm going to skip. Not because they're not important, but because this is something that you can pick up yourself, and I don't think that we'll need them for the rest of the syllabus. Okay, so we'll skip level curves and contour plots for now, and we'll go straight to limits of functions. Right. So if you recall, for functions of a single variable, right? How do we define limits for functions of a single variable? So if you start with the limit as x goes to a of f of x equals L, what does this mean? Right? What does it mean? It means that for every delta greater than 0, meaning for all delta greater than 0, there exists epsilon greater than 0 such that if f of x, this in green, if the distance between f of x actually, let me put it this way. If x is in the domain of the function f, right, then f of x minus L. Actually, I think we should be reversing. Actually, let me just start this again. This epsilon, this should be for all epsilon greater than 0. Then there exists a delta greater than 0. Actually, so for all epsilon greater than 0, there exists a delta greater than 0, such that if x is in D, then f of x minus L then x minus A less than delta. If this is the case, then it's less than epsilon, right? I mean, if the distance, so if I give you any small number, epsilon, any small positive number, right? So epsilon is a small positive number. Small positive number, right? Epsilon, right? So if I give you a small positive number epsilon, you can find a small positive number delta, small positive number delta, such that if the distance between x and A is less than delta, this tells me that the distance, this is the absolute value of x minus A, so I can say that this is the distance between x and A is less than delta, then the distance is less than delta, then the distance between fx and L is less than epsilon, right? So so if the distance between x and, so this is how we learned, this is what we learned about, this is how we define limits of single variable functions. Now we will come up with an analogous definition for limits of multivariable functions. So the definition is as follows. Let f be a function of two variables, right? And let the domain of f, right? Let the domain of f contain points arbitrarily close to AB. Let the domain of f contain points that are arbitrarily close to AB. AB, right? Then we say that the limit as x goes to A, as xy, remember we're dealing with Cartesian pairs here, right? So f of xy equals L, alright? If for every epsilon greater than 0, there exists a delta greater than 0 such that the distance between x minus a, x and a, and I mean this distance is less than delta if this distance is less than delta, then this distance f of x y minus L is less than epsilon. Right, so if this distance, then of course xy is in the domain xy is in the domain of f. Right, so you notice that in the previous definition we had a distance between x and a. Now we're dealing with a distance between xy and ab. So for that you have to use Pythagoras' theorem, right? Pythagoras' theorem to find that distance. Okay, so now that we've defined the notion of a limit, right? When it comes to multivariable functions, let's look at this. Let's look at this diagrammatically. Okay, so let's look at multivariable limits diagrammatically. Right, so if you have remember with single variable calculus we try to narrow down the interval of f of x about the limit, right? So f of x in single variable calculus we had this, right? And then this gave us L minus epsilon f of x, L plus epsilon. I mean, we found an interval for f of x about L, right? An epsilon interval of f of x about L. And for every epsilon greater than 0, we found a delta interval, right, about a, right? So a plus a x delta plus a, right? For every epsilon there exists delta such that this is the case, such that if this is the case, right, then you get this. Okay, so that's how we define it in terms of single variable calculus. Similarly, instead of this interval, right? Instead of the interval, what we are going to do, what we do is we think of the Cartesian distance, meaning the distance along a straight line between the 2 points. We use Pythagoras theorem between the points AB and XY. What is the distance between AB and XY? Distance between AB and XY is, of course, the square root of x minus a squared plus the y minus b squared. Right, so that's the distance between AB and XY. Right, cool. So let's do this diagrammatically. So if you have a point. Now that point may or may not be within the domain of the function, right? The point where you're trying to find the limit at may or may not be within the domain of the function. Oh, sorry. The point I'm trying to make is this. If you're trying to find this guy, right? There is no guarantee there is no guarantee. Let me rephrase that. A doesn't have to be in the domain of F, right? A doesn't have to be in the domain of F, right? Or in our case, since we're trying to find this limit x comma y goes to a comma b of f of xy, this tells me that AB, this ordered pair, right, doesn't have to be domain of F, right? It could be, but it doesn't have to be. Right. So diagrammatically, the definition of the limit tells me. Let's sketch the domain. Right, let's sketch the domain of F. And of course, this is the range of F, right? So domain has y and x, and this is the range of F. Let's call it Z. Let's sketch this domain. So let's let this be let the shaded region be the domain of F. Right. So now let's look at this interval within the let this be L plus epsilon limit. Sorry. Let's be limit plus epsilon, and let this point be limit minus epsilon, right? So I narrowed this down, right? So this is a range, an interval within the codomain, within the range of F, right? Now I should be able to find a region within the domain that maps onto this region within the codomain, within the range, sorry. I should be able to find a circle within the domain that maps on to this range to this interval within the range. So that's by definition, right? So we'll call this our epsilon delta interval, right? So okay, so let this be our the center of the circle is of course the point where we want to find the limit. We want to find the limit at the center of the circle. So this is my point AB. Center of the circle is AB. So let's say this point here maps onto some point in this range, right? This I call the delta circle. The delta circle, meaning it has a radius of delta. Why does it have a radius of delta? Because it is defined by this inequality. Right. So the within the circle the region within the circle is defined by that inequality. Right. So something within the circle has to map onto the somewhere in this interval. That's basically what it means. Something within this circle has to map onto somewhere within this interval. That's what the definition is telling you. And it also tells you that I can make this interval, this L plus E and L minus E interval, as small as I want, but I still have to have something within that circle map onto something within that delta. So I okay, let me rephrase this. If I make this interval, right, L plus C to L minus E, if I make this interval smaller, then I should be able to make that delta circle smaller so that something within that delta circle maps onto that interval, somewhere within that interval. Okay, so if you recall from single variable calculus, we have a lot of cases where the limit at a certain point of a function does not exist, right? For example, if the left-handed limit, right, x coming in from the left of f of x is not equal to the right-handed limit, right? If this is the case, if this were the case, then this would not exist. As x goes to a, f of x does not exist. Because remember, along the x-axis, right, there's only there are only two ways you can get to a point, right? You can come in from the left, or you can come in from the right. But when we're dealing with the domains that are two-dimensional, right? When we're dealing with domains that are two-dimensional, there are infinitely many ways to get to the limit point, right? So for example, if your limit point is at AB, if this is your sorry. Just give me a moment. Okay, so recall that I said that if x goes to a minus of f of x is not equal to x goes to a plus of f of x, then the limit is x goes to a if f of x does not exist. Now, in multivariable calculus, there are infinitely many ways to get to a point. So, for example, if you have a domain, I mean in two dimensions, right? If you have Cartesian pairs, right? Let's call this the y-axis, let's call this the x-axis, and we have the domain of a function. And let's say you want to find the limit at a point AB. So how many ways are there of getting to this point AB? Well, you could choose to come through here. Or you could choose to come through here. Or you could choose. I mean, you don't have to. It doesn't have to be linear, right? You could choose to follow this direction, this curve, right? You choose to follow this curve, right? So there are infinitely many ways to get to AB, right? The point is there are infinitely many ways to get to AV. So let's say two of those ways do not coincide, right? Then the limit does not exist. So, for example, if you move along a curve C1, right, and so for example, if you if limit as x goes to A and y goes to V, f of x equals L1 as you move along the curve C1, and limit f of x equals L2, right, as you move along C2, then and if L1 is not equal to L2, then limit as x goes to y AB f of xy does not exist. Does not exist, right? So you can so the necessary condition for the limit to exist is that the whichever direction you get to the limit point, whichever curve you follow to get to the limit point, the limit has to be the same. So for example, let's look at this. Limit is we want to look at this example from Stewart's calculus. We want to show that this limit does not exist. Limit as xy goes to 0, 0, x squared minus y squared divided by x squared plus y squared, right? We want to show that this does not exist. Okay. So how many ways can we go to 0, 0? We can go to get to 0, 0 in infinitely many ways, right? We could so let's look at the point 0, 0, 0, 0. Well, let's look at the linear paths, right? We go this direction, around this direction, along the y-axis, from this direction, go from this direction. Okay, let's test two paths, right? Let's see what happens if we go along the x-axis. Let's go along the x-axis. Let's go along the x-axis, right? So when I say x-axis, I mean y equals 0. So you're going along the x-axis. So along the x-axis, y equals 0. So this is actually equivalent to finding the limit as of f of x 0, f of x 0, right? As x goes to 0. This is like finding the limit of course when y is equal to 0, right? So this is x squared by x squared, and this is of course going to give you 1. But now let's go along the y-axis. Let's go along the y-axis. Meaning x equals 0. The limit that you get when you go along the y-axis is negative y squared by y squared equals negative 1. Right. But this is not the same as the limit when you go along the x-axis. So we can conclude that the limit as xy goes to 0, 0 does not exist. Okay, so this does not exist. Now, what about so we can safely conclude that the limit does not exist, right? The limit does not exist. Okay, so let's look at the let's look at another example. F of xy equals xy over x squared plus y squared. Right? Now, of course, if you go along the x-axis, you have a limit. You have this left, right? Limit as x goes to 0 of f of xy is equal to 0, right? Then you go along the y-axis. Well, limit x goes to 0, f of xy is still 0, right? Because along the y-axis x equals 0, along the x-axis y equals 0. Now the question is, does this tell you that the limit exists? Well, no. We've only looked at two different paths. What about other paths? Let's look at let's go along I don't know, go along y equals mx, right? So that tells me that limit as xy, so what am I doing now? X goes to 0, 0 along y equals mx. So instead of y, we'll have mx. So x times mx divided by m square x square. This is x square plus m square x square. So this is equal to limit as xy, sorry, x y goes to 0, 0 of 1 over 1 plus m square. Now this depends on m. This is something that depends on m. Depends on m, right? So if I set, let's say, m equals 0, then the limit becomes if m equals 0, then the limit is 1, right? If m equals 1, the limit is 2. So you choose different paths and you get different limits. So this tells me that the limit does not exist. The limit does not exist. As the limit as x goes to 0, 0, xy goes to 0, 0, that does not exist. Okay, so let's so there's another example where the limit does not exist. There's a f of xy. You can show this yourself. Show that using the same method, then limit as x and y go to 0, 0 of xy squared by x squared plus y squared, xy squared divided by x squared plus y squared does not exist. You can show this. Okay, so I mean, all you need to do is you need to take y to be mx and see that different paths lead to different limits. So if m equals 2, you got a limit, m equals 3, you got another limit, and so on and so forth. Right, so let's look at certain limit properties right now. I mean, these are properties that you already studied in single variable calculus, and I think they're going to be useful in multivariable calculus as well. So this is page 955 of Stewart's calculus. Assuming that the limits, individual limits exist, then the sum of two limits, the sum of the limit of two functions, the limit of the sum is the sum of the limits, the limit of a difference is the difference of the limits, the limit of a constant times a function is the constant times the limit of the function, the limit of a product is the product of the limits, and the limit of a quotient is the quotient of the limits, provided the limit of the denominator is not 0. Okay, and you have these special limits. Limit as xy goes to a, b of x is equal to a, limit of xy goes to a, b of y is equal to b, and limit of xy is equal to a, b of c is equal to c. Okay, so and a polynomial function where is when it comes to functions of two variables is a sum of terms of this form, c x and y n, right? So so instead of once a polynomial in one variable, we have polynomials in two variables. So you have m equals 1 to, let's say, a k, and n equals 1 to l. So you have c mn x m y n. These guys are the constant coefficients. Right, so you have terms of this form, right? These are polynomials, right? So, for example, this guy is a polynomial. So, in this case, c 4 0 is equal to 1, c 3 2 is equal to 5. I mean, this is just notation I made up on my own. C1 4 equals 6, C0 1 equals -7, and C0 0 is equal to 6, and of course all the other c's are 0. And a ratio of two polynomials is known as a rational function. Okay. So in the special limits in 2 along with the summation with the limit laws allow us to evaluate the limit of any polynomial function p by direct substitution. Alright, so you have these limit laws, right? These limit laws, right? And these rules, right? These laws and these laws, these limits, they tell you that the function of polynomials should give you I mean, this is one way of saying that they're continuous, right? That you can evaluate the function, the limit of a polynomial by direct substitution. And if you have a rational function, you should be able to evaluate, PAB over RAB, provided, of course, that RAB is not equal to 0. So P over R. So this is in fact the definition of continuity. This is continuity, meaning the polynomials, they're continuous polynomials. They're continuous functions, even when it comes to two variables. Right. So for example, if I have a limit that looks like this, x squared y cubed. Okay, so what's the difference between, by the way, these rational functions and this one, as x and y go to 0? Why doesn't the limit exist here? I mean, why doesn't, for example, x? Why can't we just evaluate this by plugging in x equals 0 and y equals 0? Right? That's because, well, if x equals 0, y is equal to 0, denominator becomes 0. Right? So, and for us to be able to use these rules for rational functions, the denominator cannot be 0. Right? So what they did is they just plugged in x and y to get the limit. Okay, so the next thing we do is we're going to use the squeeze theorem to evaluate limits. If you recall the squeeze theorem, right? This squeeze theorem, it tells you, what does the squeeze theorem tell you? The squeeze theorem tells you that if you're able to squeeze a function, I mean, when it comes to single variable calculus, if you're able to squeeze a function between two different functions, right? So you have gx, fx, hx, right? And if you have limit as x goes to a of gx equals L, and you have limit as x goes to a of hx equals L, you may combine the two to give you the limit as x goes to a of fx equal to L, right? You can do that. Right? Now, that's the squeeze theorem. So we can also apply the squeeze theorem to limits of multivariable functions, right? So if you have g of x, y, f of x, y, and h of x, y, and if you have limit as x, y goes to ab, g of x, y equals L, and limit as x, y goes to ab of h of x, y equals L, and the limit, then you can safely say that if you can safely combine these two facts to state that the limit as xy goes to ab, f of xy must also equal L. Alright? That's the squeeze theorem when it's applied to multivariable functions. So let's look at an example from Stewart's calculus. So this example involves the use of the squeeze theorem. So the function given is f of xy equals thrice x squared y, x squared plus y squared, right? So this is, we want to find this limit if it exists, right? So now how will we find this? How will we find this limit? So recall that x squared plus both x squared and y squared, x squared is greater than or equal to 0, and y squared is greater than or equal to 0. So this tells me that this tells me what exactly? This tells me that the modulus of y, right? The modulus of y is less than or equal to the modulus of y square, for example, right, is less than or equal to okay, so the modulus of y is less than or equal to modulus x square, the square root of x squared plus y square. Alright? This is less than or equal to x squared plus y squared. It also tells me that the modulus of x square is less than or equal to x square plus y square. Okay, cool. So you have thrice x squared y over x squared plus y square. Now if you take the modulus of this guy, this is equal to thrice x squared by x squared plus y square, right, times the modulus of y. Now this guy, x squared, this guy has to be less than or equal to 1, right? This guy has to be less than or equal to 1. This tells me that this is less than or equal to 3 times the modulus of y. And if you get rid of the modulus signs, you end up with negative 3 modulus of y, and then 3 x squared y, so x squared plus y squared, 3 modulus of y. But then the limit as x and y goes to 0, 0 of the modulus of y is 0, right? And the same can be said for minus y, right? So you take the limit of this as x y goes to 0, so you take the limit of this as x y goes to 0, 0, and get 0. So then you get limit x y goes to 0, 0 of 3x squared y zero. Right, so this was an application to squeeze theorem. With the same example, what the book does is also, as towards calculus, what it does is also proves the same limit using the epsilon delta definition. I expect you to go through that example and try to work it out for yourself. And at the end, of course, there's the idea of continuity, right? Continuity is defined in the same way as it is for single variable functions. You have limit for single variable functions. You have limit x of a as x goes to a, f of x. If this is equal to f of a, then this tells me that f is continuous at x equals a. Right? Now, if you have a limit as x comma y goes to a comma b of f of xy equals f of ab, then this tells you that f is continuous at xy equals ab. Right. So we've looked at examples of continuous functions, multivariable functions, in this lecture. For example, you have the you have functions of we've looked at functions, the polynomial functions that are continuous, and one example for continuous function is so if I set f of xy. Let's look at this function, right? Let's redefine an old function, right? It's if f of xy, x squared minus y squared, x squared plus y squared, right? So we're going to find out that this is discontinuous, and then we're going to redefine it and find out that it's indeed continuous. Okay, so the function is f is discontinuous at 0, 0. Why is that? Because it is not defined there. Xy is discontinuous at 0, 0 because xy is not defined at 0, 0. Now, however, on its domain, since f is a rational function, remember rational functions are polynomial over polynomial, right? Since f is a rational function, on its domain it is continuous. But if we let now what if we let g of xy be x squared minus y squared if x and y are outside the origin and 0 at the origin? Does that make it continuous? Well, no, it doesn't make it continuous at 0, 0. Why? Because at 0, 0 the limit, this guy, I mean not at 0, 0, as x and y tend to 0, 0, this is not defined. But outside of 0, 0, yes, f is continuous. How about this rational function? Thrice x squared y by x squared plus y squared. F is continuous for xy is not equal to 0, 0, and is equal to a rational function there, right? If x and y are not 0, 0, then of course f is continuous. And and remember we figured this out, that limit of as xy goes to 0, 0, f of xy is 0. We figured this out using the squeeze theorem, and f of 0, 0 is equal to 0, and so f is continuous there. Now, if you combine two functions, the function composition, the composition of two functions is continuous. Just as the composition of two functions in a variable calculus is continuous. Okay, so what about this guy? E to the negative x squared plus y squared. Is this continuous? Well, this is a polynomial. Alright, so this is continuous. And e to the negative t is also continuous. Right, so the composition of these two, e to the negative x squared plus y squared, is also continuous in R2. And notice what happens as anywhere you approach the limit value, remember continuity implies that the limit value equals the function value. Right. So now where is this guy continuous? Arctan y by x. Well, again, arctan y by x is rational and continuous everywhere except where x equals 0. Right? And GFT arctan t is continuous everywhere. The arctan function takes on everything in the domain. Right? So arctan y by x is continuous. The composition is continuous everywhere except where x equals 0. And so, so that tells you, I mean, right above the yx, if you notice the, I mean, obviously it's not defined on x equals 0. So by x equals 0, we mean the y-axis, right? And notice what happens right above the y-axis, as it goes above the y-axis. We'll have a look at this on Mathematica. Anyway, okay, so similarly, everything that we've done, everything we've covered in this section, right, can be applied to functions of 3 or more variables, right? So how do we define a function of 3 or more variables? So a function of 3 or more variables takes an ordered 3 tuples, right? 3 tuples, ordered 3 tuples, the x, y, z. Again, ordered means that this order x, y, and z matters. 1, 2, 3 is not the same as 2, 3, 1, or 3 to 1. Right? So as x, y, and z go to a, b, c, right? So then so this means that if x minus this distance is less than delta, this implies that this distance is less than epsilon. Again, continuity is defined analogously as x, y, z goes to a, b, c of f of x, y, z, then this is equal to f of a, b, c. This function, for example, is a rational functions of 2 variables, so it is continuous everywhere except where this is equal to 1. Right? X squared plus y squared plus z squared equals 1. So it is discontinuous in the sphere with center, the origin, and radius 1. Okay, so in fact, we can represent the domain of the argument of a function of many variables, right? Of let's say n variables by x, a vector x, right? So this is equal to x1, x2, dot xn, right? So as limit, so we say that the limit x goes to a vector of f of x, right? So we've studied n equals 2, and we've just now looked at n equals 3. So this is equal to L, right? So remember, this is a vector, this is a vector. This argument is a vector, right? And this is equal to L. This means that if x is part of D, D is of course a subset of Rn. Right? D is a subset of Rn. So for every epsilon greater than 0, there exists a delta greater than 0 such that x minus a, the distance between the vector x and the vector a being less than delta, then implies that if this is the case, then f of x minus L has to be less than epsilon. So this is the most general case, right? This is the most general way of stating it. Right? Now, if n equals 1, for example, you'll have if n equals 1, you have single variable calculus. If n equals 2, you have functions of two variables, and so on and so forth. Okay, so that's it for this lecture. We've covered 14.1 and 14.2, and next week we're going to look at partial derivatives. Right? Partial derivatives. We're going to define what the partial derivative is, and we're going to try to figure out why this is useful. Okay, thank you very much.